All right, I think that we're at the top of the hour, so we'll go ahead and get started. My name is Daniel Gross. Today's presentation is titled, Where's the Beef? First, introduce myself a little bit. I'm an IT engineer at the University of Kansas. And this help. There we go. My responsibilities as an IT engineer at KU in a security-related department is I identify, develop, implement, and support security technology and methodology. That focuses on endpoint, particularly endpoint detection and response, antivirus, attack surface management, disk encryption, mobile device management, and also consult with other IT units on different business processes and the infamous other duties as assigned. If you were in the privacy presentation, that person rightly stated that they are not a lawyer. Relevant to our conversation today, I am not a network engineer. My role focuses on endpoint. That's where my focus is. That's where my skill set is. Networks that are larger than 5 VLANs or 2 ISPs are a little bit scary for me. Obligatory iOS joke from Andy Dwyer. I don't know why all the network engineers have iPhones, and at this point, I'm too afraid to ask. Like all interesting sort of topics, I started with a problem, a perceived problem. I had trouble reproducing IPS block events on different network subnets. So the way this would go is a trouble ticket would come in from a support unit saying, hey, please unblock website XYZ for such and such business process. After checking logs in the IPS, I could see that the traffic was getting blocked, but was unable to reproduce the block behavior on a different endpoint. After a couple of times of that happening for a few different things, I started thinking to myself, oh, that's weird. So I started to come up with a plan of how I could get to the bottom of identifying where the weirdness is coming from. It is, of course, the start to many a rabbit hole. There's, of course, a lot of different things that this kind of behavior could be. Could be that we blocked a CDN in the IPS. We received some flawed definition update from a vendor that is blocking a CDN, or maybe there's a weird subdomain that only presents if you do some specific action that wasn't shared in the trouble ticket, something like that. Could be working from another institution's network. Maybe that other institution is doing something weird. The final thought that came to mind was, what if all egress network traffic isn't being treated the same? And of course, we have different satellite locations that egress differently, but this is more main campus type stuff, where there's not really a good reason why that traffic shouldn't have been blocked based on the observed behavior. So from the problem came a solution. I'll build a botnet. No, but really, I'll write a PowerShell script. It's going to run a simple invoke web request command to a canary domain that I block in the IPS. The script is going to use the return status code to tell if that endpoint, wherever it happened to be in the world when it ran that script, returned a successful status code or some kind of a different status code, maybe 400, 500, whatever it may be. And if I load that into MECM, maybe it's now just MEM, they rename it too frequently, as a configuration baseline, then I can get a handy compliant and non-compliant collection out of that, just from the PowerShell script. I can tell this machine was able to reach my canary domain, this machine was not. And then I can start investigating from the endpoint side why that might be. So write a PowerShell script, great, that covers the endpoint. I had the idea of what if I could see both ends of that traffic? So I can see the NAT egress points. I can see where that's coming from in the world. I have logs both on the endpoint as well as on the server side. I can compare. I can get a more holistic view of that network traffic. So requisition a server to host a website, not on our network, because we want this to egress out to the internet just like any other thing would. So what if we host it in our preferred cloud environment and just use one of their public IPs? I could then use a reverse proxy to route the traffic as desired, or add an SSL certificate, something like that. easily. Next step, come up with a catchy domain to block. Blockthis.ku.edu has a nice ring to it, so that's what I ran with. And then after that process runs for a while, after that, I have gathered a volume of information, of incidences of this happening, I can then analyze the logs using that visibility from both the endpoint and the server, and in the IPS, hopefully, we can get a more holistic view of how that is egressing from campus and identify any egress NAT points that might not be covered or that might be problematic. So a while back, I'd heard about a security tool called BeEF. And this is copied directly from BeEF's website. It's a little bit difficult to read on the pretty picture, but just real quick, BeEF is short for the Browser Exploitation Framework. It is a penetration testing tool that focuses on the web browser. There's a little bit more about why it's important, but the important takeaway is it's an easy to use malicious web server. Jackpot, I needed a web server. Why not have some additional capabilities as well? You can find their website at beefproject.com. So a little bit more about the why. Why choose BeEF? Why not just use Nginx? That would suffice. I could even have a DNAT point on an Azure firewall, not a real web server, but as long as there's requests coming in, I can see the requests, where they're coming from, things like that. There's both short-term use case and a long-term potential benefit. So today, I get server-side logs showing NAT egress points for campus traffic that may bypass expected security controls, namely IPS. I can get experience with an offensive security tool and by extension, adversarial capabilities. What are the bad guys capable of with a tool like this that can just spin up off the shelf, as we'll get into later. And I can also gain some experience with containerization technologies and risks of misconfiguration of containerization technologies. In the future, what we could do is self-hosted phishing landing page with endless customization. Going beyond that a step further, really realizing the capabilities of BeEF, more targeted red team type activities, including interactive self-phishing. Of course, disclaimer here, make sure that you do all of this with consent and CYA. Another potential use case would be to redirect canary tokens or documents. Those are things that we put out there that we intend for an attacker to find and try and leverage. What if we direct the attacker to our malicious website to gather some intelligence about them? What's their source IP? Feed that into a IPS or to a M365 conditional access policy and block any logins from those malicious actor IPs before they even try to exploit anything. So a lot of potential there beyond just what an Nginx container could do or a simple web server could do. And I've thrown around this term a little bit, just make sure everybody's on the same page about red team and blue team. Red team is more offensive security, penetration testing. They are doing things like social engineering or things like that. Blue team being more the defensive responsibilities. So doing things like ensuring that endpoints are properly configured, like me. Or making sure that our security technologies are behaving as expected. Sorry, I don't know why that keeps zooming. Anyway, moving right along. So why would a blue team use offensive security tools? We've already touched on this a little bit about the benefits that of using a BeEF server over just a simple web server has, but more holistically, knowing yourself and knowing the enemy. If I am able to do it, the attacker probably can as well. By identifying the weaknesses ourselves, we can take steps to mitigate them, making the attacker's job more difficult. That's the end-all be-all of security. Just make it harder for the attacker to accomplish their objectives with us than it is with somebody else. And also to know the enemy, knowing how to use the tools a malicious actor might use to attack the organization. And there's probably a lot of this already happening in the organization. Things like sort of blending the red team and blue team responsibilities. Things like identifying and vulnerability scanning devices on your network. That's reconnaissance. Using your SIEM or EDR is probably mapping attack framework to EDR events. This is a Word document in an email. Is this spear phishing? It matches the attack framework for it, so it could be. If you're doing things like proactively phishing your users, are they clicking those links, perhaps to a BeEF server or something else? Or things like external attack surface reduction tools like Shodan or CISA scans. And also third-party penetration tests, sort of interacting with the penetration tester, asking them, hey, we have this alert. Is this perhaps caused by your penetration test? That kind of back and forth interaction that blends that red and blue team mindset, making it purple, which is appropriate for the venue of our conference this year. Moving right along. Is it really a cybersecurity presentation if nobody mentions Sun Tzu? So obligatory. If you know the enemy and you know yourself, you need not fear the result of 100 battles. If you know yourself but not the enemy, for every victory gained, you will also suffer a defeat. If you know neither the enemy nor yourself, you will succumb in every battle. Sun Tzu. So what this is advocating for is a blended approach, not just red team, not just blue team, but blending those two kinds of mindsets to further the business goals. And you'll notice that some of these slides have that kind of theme as well. I just wanted to briefly mention a little bit about the attack matrix. This is kind of a very handy matrix for mapping different activities to what the attacker's objectives might be. So we talked about reconnaissance, so active scanning, passive scanning, figuring out what's on the network, what's where, trying to get initial access to that environment, perhaps trying to phish your users, things like that. That's all great, that's all fantastic. And we have tools that are trying to map this, map behaviors rather, to this framework, and that's helpful for understanding attacker objectives. We also have the defend MITRE framework, which is the opposite side of that coin, which is what activities should the defenders be doing? What are their objectives? What are their goals? But those both focus on attack and defend. They're not blended. They're not working together. They're not purple. Enter the, this out of the way. Enter the Lockheed Martin cyber kill chain. I love this. It does a great job of sort of blending attacker objectives and defender opportunities to disrupt the attacks. We'll just go briefly through it. There's 7 steps. The idea is that the attackers need to accomplish every piece of the kill chain in order to fully realize their objectives, i.e. deploy ransomware, whatever it might be. And it maps out what the attacker is thinking at that time and what the defender should be thinking at that time, how to disrupt that attack, how to prevent the attacker from accomplishing their objective. So we'll jump right in. First, reconnaissance. You need to know what's where. You can't attack something that you don't know about, right? So the defender is detecting that reconnaissance or attempting to. What is scanning my perimeter? Is that Shodan or is that a adversary that's running that port scan across our entire subnet? So things like making sure that you're collecting visitor logs is very important for the defender to detect even after the fact that an attack has taken place. Those URL strings are very handy. Sorry, I think the touch screen is what's causing that to zoom in like that. Can we disable that?
Go find someone
okay
to try, because it does seem to be like, so let me go see if the one can.
Great, thanks. All right, moving right along. Reconnaissance. We all kind of have an understanding of what that reconnaissance step is. Okay, can't go to the next slide.
Don't worry about it. Yeah, we're here to listen to you.
All right, fantastic.
Yeah.
So second step of the cyber kill chain. I'm gonna pull this up over here as well. That is difficult to watch. All right, second step, weaponization. So I know it's out there as the attacker. I have perhaps identified some infrastructure that I am more interested in. Maybe it's an ADFS server, something like that. I know what it is running. Maybe it's Apache or something like that. I then am going to be looking for a way to exploit that asset that the entity owns, that thing that I'm interested in. On the defender side, this is an essential phase to understand. You can't really detect the weaponization. You can't find out, oh, adversary XYZ is searching for Apache exploits. That's not realistic. But what you can do is infer this is where it gets into the reviewing Apache logs or things like that, watching for really long, weird strings in a post command that might be evidence of an RCE or something like that having taken place. Detections against weaponizer artifacts are often the most durable and resilient defenses. So we're trying to sort of stop that at this phase before they've had any real impact. Moving right along. Phase 3. I use the touchscreen. Phase 3, delivery. We're going to launch the operation. The adversaries are going to be conveying the malware to the target. Maybe they've done a proof of concept. Maybe they've discovered, yes, this is actually vulnerable to my exploit. I've run an RCE against this web server and I've gotten back a ping that I expected. So I can tell that that is indeed vulnerable and it will do the thing that I expect it to. That my weaponized malware is going to be doing. This is where it begins in earnest. That's why we wanted to stop this before we got to this point. On the defender side, this is first and foremost an opportunity for defenders to block the operation from having any real impact. A key measure of effectiveness is the fraction of intrusion attempts that are blocked or at the delivery stage. So I have identified that there's a patch available for this server. I've applied it. We saw perhaps some anomalies in the logs, but we found that there was a patch available. We applied it, and now there's no longer an active vulnerability on that endpoint. This is very important for the defender to be aware and constantly monitoring for this activity. Next, stage 4 is exploitation, gaining access to the victim. From the adversary side, they are trying to exploit a vulnerability, be that people, be that technology, to gain access. That could be just asking Bob for their password, and they give it to them. There's also a lot more complex ways that this can happen, where they are exploiting a 0-day or perhaps an unpatched vulnerability that we haven't caught. They may develop those 0-day exploits or purchase them from a broker, but more likely they're going to be just phishing. Just ask somebody for the password. People have a genuine desire to be helpful, and that applies to situations where it might be in their best interest to not be helpful. From the defender side, what we're doing is traditional hardening measures to add resiliency. But it's more than that. If you have if you participate in the internet, then you definitely need to have custom capabilities. You need to build to assume that there's going to be an exploit taking place. You need to segment these systems so that one cannot compromise another. Or if you were at Check-It KU, build tools like automatic network isolation. When there are certain kinds of, that I gave a presentation about at the last Check-It KU, if you can network isolate a machine that is behaving anomalously, that has signatures of being exploited, you can shut that down right at that stage, cut off any further intrusion by the attackers. Moving right along, we come to step 5, installation. So this is where I start to, as the adversary, this is where I would start to actually exploit that vulnerability with the purpose of gaining access. That could be the human gave me a password, so I log into their Azure tenant. That could be a web server that's unpatched sitting on the fringe of the network. But this is where the things start happening in earnest. And for the defender, pardon me, fall behind there. There we go. So this is where I've done the exploit. I'm now going to try to establish a persistence. I know that the server is vulnerable, but I don't know how long it's going to be vulnerable. It's going to be important to build my own capability of controlling that machine. Otherwise, that could be opening a netcat shell. That could be any number of different technologies that are. Sorry, it's the touch screen. It just keeps on zooming in. It seems to be on this one because it pops up and then. So, yeah, great, thanks. Great. From the defender side, this is instrumentation on the endpoint, namely EDR product, to detect anomalous behavior. This could be a log centralization, a SIEM tool, where we're analyzing logs from all of the server fleet, and we're analyzing for anomalous things. This could be where we identify that server XYZ is now listening on a new port in a high range that's unexpected, things like that. So we built our endpoint control. Moving on to stage 6 is command and control. So this is where my backdoor that I planted maybe starts beaconing out to my control software. Maybe we're doing DNS tunneling, or maybe we're sending some strange HTTP post commands and listening for responses to that session. Things like that from the adversary side. From the defender side, what we're doing is reviewing logs. This is why it's very important that our IPS is as comprehensive. There we go. Is as comprehensive as it can be. If we're seeing strange DNS egress that's to some strange server somewhere out in the world, this is where we can. This is where we can try and catch that anomalous behavior and perhaps implement some of those custom controls that we alluded to earlier, maybe automatically isolating that endpoint until we can further review it until a full scan completes or something like that. And then we come to stage 7, which is actions on objectives. This is what the adversary has been trying to work for through the entire kill chain. This is what their end goal was. This is where they have interactive access to some of your infrastructure. They're accomplishing what they set out to do. What happens next could be any number of things. Maybe they're still going to be watching for a while. Maybe they are going to be exfiltrating your data at this point. Maybe they're going to be staging some ransomware on open FTP servers on your printers, things like that for distribution later. As the defender, the longer that this stage goes on, the greater the impact. The more they're able to exfil, the more they're able to stage malware in the environment, the more they're able to move laterally within your environment to build additional different sorry, lost my phrase there, but establish additional beachheads in your network. So if you find and shut down one, they might still have another one that they have control over. And at this point, it could be a game over event. They've deployed the ransomware, they've accomplished what they set out to do, and now they sit back and wait to collect their money. That still seems to be doing it. Anyway. Must be. Oh, it's not about that. Move over here. Nope, still doing it. All right. Anyway, so I appreciate you going through the cyber cold chain with me. I think that it's a great way to easily view and compare what the attacker's objectives and the defender's objectives are at these different stages. I think that it is a great approach. It has a great way of sort of showing the importance of thinking about both the attacker and the defender's perspectives. So hopefully I've convinced you all that purple teaming is what we need to be doing. Next up, I'll talk a little bit about the endpoint configurations for our PowerShell script that we talked about a little bit ago. In MECM or MEM, whatever they're calling it these days, there is a item called a configuration item. Its purpose.
So sorry that we can't get that to stop doing that. I know as a presenter, I know how difficult that is to be distracted.
Thank you. It's all good. So MECM has configuration items. These are basically intended for compliance checks. Maybe you want to confirm that all devices in your organization are properly applying group policy. You can easily build configuration items that look at your group policy, import those as a configuration item, runs a small script to check or checks for the registry values that you expect so that you can make sure that, yes, this device is configured as it should be according to the group policy that we've set out. I'm going to use it for running our PowerShell script on a schedule. Basically, if you can script it, you can evaluate it. The configuration items are all wrapped up into a single configuration baseline. For our purposes, I only need it to do one thing. I need it to run that invoke web request out to my canary domain and confirm if that was successful or not based on the response code. Gesundheit. And by controlling the true or false exit status of my script, then I can return that compliant or non-compliant value that we're looking for to build our collections, to see who was able to reach that domain that shouldn't be able to. So next, we have our configuration baseline. It consists of a single configuration item that we're testing against. And at this point, we can deploy it to a collection. This would be a testing collection at first, make sure that we don't unexpectedly restart the device every time it runs, things like that. And we can also define the frequency to evaluate that condition against. I chose once a day, so there's a few thousand devices reaching out to that canary domain once a day, wherever they happen to be, and that will return a compliant or non-compliant response. And then from this, I make my compliant and non-compliant collection. I weed out the ones that are in unexpected network locations, maybe a satellite campus, something like that, where I don't actually expect that traffic to route through certain things. So that's the endpoint side of this. That's all that we need to get going. Next is the part of this that was less familiar for me. And so we have a crawl, walk, run. So our crawl in this case is Docker CLI. BeEF can be deployed with as a Docker container. And with that, you don't have to worry about the Ruby dependencies and all kinds of random other package dependencies that would be a nightmare to maintain. Once we've crawled, Docker Compose is a great way to walk. Say, for instance, I want to have a Nginx container in front of our BeEF server and reference the BeEF server in a script. It has a handy hook.js. So now I have 2 Docker containers working in tandem, rather than a slowly and frequently updated BeEF server sitting exposed to the internet. I can just have a disparate web server sitting as a middleman who's kind of brokering those connections back. And then running. In this project, running is uploading our images to a container registry so that we can make them more portable, using a GitHub runner to automate pulling down updates and updating our container, our customized container in our registry. So crawling, as we talked about, looked like Docker CLI. It's really gross to try and manage something only with Docker CLI on an endpoint. It involved, my initial setup involved a lot of manual editing using Docker exec to get a shell in the container and making manual changes. I built a cron tab that would restart the container after the host restarted to apply updates. As you might imagine, this was very onerous to maintain, even with some cron tab automation. It was definitely not maintainable. So then I was introduced to the wonders of Docker Compose and infrastructure as code. So I can define with a single YAML file all of the containers that I need, all of the ports that I need to forward. I can handle my restarts. I can handle passing through volume. So I can have config files stored on the host that are passed into the container to apply these different configurations, both for my Nginx front end as well as my BeEF server on the back end. This was a wonderful, development and made everything a billion times easier. And then running.
I would say, I think maybe if we get it where we want it and stuff. Oops.
Yeah, it seems to be happening even when I'm not even touching anything. So yeah.
Try. See, it's still doing it. It's like.
Yep. Is there a USB port in the back that, there we go. That should do it. Oh, well, maybe not. Promising beeps. But
Yeah, it's something to do with like it's picking, somehow it's picking up something that is not.
yeah, Phantom touches. It's
Yes.
Yeah.
And then, I don't know, maybe try just like if it'll stay there, maybe just try the arrow keys to move and see if that will do it for you.
Now that it's unplugged, it seems to be a little bit happier.
Okay.
Oh, I spoke too soon. Oh well.
Okay.
We'll
sorry.
soldier on here. So running. Oh, but now I need to do this. There we go. All right, so running on this came as a necessity rather than as a preference. As we were standing this up, I talked about how this was a on-premise single server running a few Docker containers. I was then advised that our original implementation for how we were going to flow the traffic out of campus and then back into campus through a DNAT point on an Azure firewall was just not going to function. That traffic wasn't able to traverse back down the VPN tunnel because that was additional attack surface that was not tenable. The solution was already present. It was already built into the architecture. Docker is made to be portable. Theory is, of course, different from practice, and there's risks from configuration pitfalls. One of the biggest ones being, don't put secrets in your container image. You don't want your SSL private cert to be sitting there in a Docker image uploaded passively to a registry. There are specific ways to safely import those secrets. And there's a lot of, the easy way is frequently the most insecure way of handling that. So I'll go over a little bit about how we migrated this first. In Azure Container Registry, here we come. Now here's where the zooming would actually come in handy. I have a running Docker container. How do I make a image out of my running Docker container? It's actually very easy. There's a very specific command, docker commit, that can allow me to take a running container, take a snapshot of it, and make a new image out of that. And then I can tag it with my versioning controls. And you can see here, after my Docker commit message, I then have a new locally stored image in my local repository that my system is now aware of. Once I have that image local on that machine, I can then tag that image with the full URL of my registry, in this case, Azure Container Registry, that is going to store my image. Once I've tagged it, I do a Docker push after logging in, and voila, I have an exact replica of my running Docker container that was on premise in an Azure environment that can be deployed with a click of a button. Now, we talked a little bit about some pitfalls there, namely storing secrets, things like passwords, things like certificates, things like that in a container, all being very bad. So with Azure Container Registry, when you build, once you're building your deployment, you set up variables, environmental variables, and reference those in your files. So you have a redacted reference pointer to an environment variable in your configuration file, or perhaps in your where your certificate should be, and then you just pass that to the container at time of startup, and that safely handles all of those secrets ingestion. So we have our Docker image in a container registry that can be referenced in a cloud environment, just keeping all of the apples together. Azure Container Registry, let's use Azure Container Instances. So I build, just a very simple form. It just references my private repository in Azure, pulls my image. We can see it's the same exact one, and give it a network. There we go. You could just put it out there on the internet. Like we talked about, it's best to control ingress to your container. So we put it in a private VNet, and we kept on using our DNAT rule to redirect that traffic. Because it doesn't need to traverse back down the VPN tunnel, it just needs to traverse to a different network spoke in Azure. We can build this in a more secure way, where all access from the internet to this potentially vulnerable container is handled through a broker, through the DNAT rule and the Nginx container in front of it. I do have just a couple of notes here of lessons learned from building BeEF with operational security in mind. A lot of times offensive tools are built to be hot rods. They're not built with operational security considerations. So as we talked about, using that separate container, in this case, I chose Nginx because it's nice and lightweight, doesn't need a lot of resources to handle a large amount of temporary, ephemeral inbound requests. And so my static HTML site with an Nginx in that Nginx container just needs a simple HTML tag to reference the hook.js script that is on the BeEF server. And so this traffic between the Nginx container and the BeEF server is all happening in a private VNet. we're less concerned with people directly accessing it. And bonus points if you rename that hook.js to be less conspicuous than hook.js. There we go. And next up, the BeEF server's config.yaml lives in that container. It controls the behavior of your BeEF server. There's a lot of non-defaults that you will want to configure. And as we talked about earlier, that can be passed as a volume mount if you would like, or an environment variable to simplify your configuration build, to make it repeatable. There we go. Another is restrict what source addresses are hooked to your own known IP ranges. You don't want to be hooking strangers on the internet. We have a very specific use case for this, and we want to make sure that we restrict it to known addresses that we control. There's also exclusions that you can carve out from there, but very important to control that hooking subnet to just what you expect. The Nginx logs will tell you what all is reaching it, but we need to make very sure that we're not just hosting this out and hooking unexpected strangers. Another important consideration is controlling your own infrastructure. So there is an admin interface that is displayed as a HTML website where you can configure or interact with your hooked browsers. So restrict that if you can to localhost or a specific small range. We're talking /32s like you see in the example. The preferred way to set this up is to allow only localhost connections. So the idea if this was sitting on a standalone server would be I SSH in and and then redirect that management port to SSH tunnel that traffic to localhost so that I can still access the server through an encrypted tunnel. Restricting who can access that admin interface is very important because we don't want attackers to find this and then start controlling it. Also very important is if you're going to allow non-local host connections to configure certificates for TLS. By default, it uses HTTP. Very easy to sniff that traffic. It does include capabilities of it does include some capabilities for TLS encryption in the container, and ingesting public and private keys to allow that to work is easily accomplishable, like we talked about earlier, with the volume mappings or with environment variables that reference those. And last but not least, certainly not least, is change the default password. It will literally stop. It will stop and yell at you and not start until you do change that in that config.yaml. By default, it's just beef, beef. Come on. So definitely do change that. That's an excellent opportunity to test out environment variables. It's an easy, did my environment variable end up where I expected it to be? Does my container start? If yes, it probably wrote successfully. If not, it probably has a problem. And with that, eventually, there we go. Thank you for listening. And thank you for your patience. Yes, Joel.
So when you started some of your initial testing, describe some of the data that you were able to get from these. So you set up a script, it's going out and touching the server. So describe some of the data that you're able to get from JavaScript, so virtual browsers.
Oh yeah. So like what data is, what kind of information can I tell about a system from once a browser has been hooked?
Typically,
Yeah. So from the BeEF side, things that you can see are public IP. That's, to be expected. I'm interacting with something, I need to know how to get back to it. Some other things include if you've ever visited if you've ever visited one of those websites that shows you your URI string, your basically what details about your computer, about the browser that you're using, about the kind of system that you're using. Is this Mac OS? Is this Linux? What's your screen size? What's your resolution? Is it a 4K monitor or is it a 480p potato? A lot of detail about the endpoint is revealed through just browsing the internet. And this is a great way of indicating just how much of that data is presented.
So in your analysis, of your use case, were there any other features inside the plugins, for instance, that you thought would have value for this project?
So for now, this is just stock standard BeEF. We haven't added in, there are a lot of Metasploit modules that are designed to interact with BeEF if you want to get a little bit more complex with it. That extends the capabilities of BeEF significantly. Built in, you have all the usual things that websites can request: desktop notifications, access to your webcam, access to your microphone, a large number of different kinds of things that browsers can already prompt you for as you're visiting different websites.
As a vendor, now that you've seen kind of how it works, have you thought of how we can defend, how a person can defend against this type of?
Absolutely. I've actually built a number of custom advanced hunting detection alerts that, so what I did was I found that there were a few JavaScript libraries out there that try to pop your browser full screen. If you've ever seen the full screen, call Microsoft, you've been hacked, trying to detect that based on observed behavior. Frequently, that's not the kind of thing that generates an alert in our EDR, but it is, out of the box. But it is the kind of thing that we can build some simple detections for, based on things like, is this browser executing something called hook.js? If so, I might want to interact with that device to find out what's going on. Or pop browser full screen.js. There's a few, a lot of, like, everybody else is just Googling things, right? So if you view GitHub and you find a few examples of how can I pop a browser to full screen and display my custom web page, then you can reference some of those same easy to find examples in a detection rule and say, hey, this is probably trying to pop full screen. Or hey, this is probably trying to scan the local subnet through my browser, things like that. Yeah, lots of opportunities out there. Any other questions? All right. Well, thanks everybody.